5. 60 something. What? 77? 5? Like that? Good job, Jeff. So the only time the bottom will change is if it's a given. Now let me show you the symbol for given. This is the word. Let me show you. Here's the symbol for given. So here's another question. Probability that they are at least 21 given. I know it's a horrible choice, but too bad. Given is just a straight line. Given that they said maybe. So what goes on the bottom? 9. So what always seems to go on the bottom? Whatever's here, right? For a given, what goes on the bottom? The number associated with what was given. Kind of makes sense. Out of those, why? Because I know that's what happened. So what goes on the top now? I heard it. What goes on the top now? 5. I love it. Because out of those 9, how many are greater than or equal to 21? 5. 5, 6. Now you guys should be able to divide by 9 really easy. 7 divided by 9 is 0.777777. I like it. So, remarkably enough, we're going to develop the formula for given. Because we have 2 examples here. We can develop the general formula just like we developed this one. So let's take a look here. So what about the probability of something given something else? What goes on the bottom? Yeah, something related to B. So what actually goes on the bottom, let me see if you guys are cool with it, is the probability of B. So what's going to go on the top? How did I get, why is this 5 and not 41? Right? Because it's greater than or equal to 21. So why didn't we put 41 up there? Because it's got to be B at the same time. It's got to be maybe at the same time. So really, oh shit, Jeff, what are you doing? I don't know. So given that B happened, so I know that B happened. What's the probability that A also happened? Well, if something in here happened, what's the only way that something in A could have happened at the same time is if it was where? In the little sliver dude, right? This doesn't have a chance. This doesn't have a chance. Good job. And this has a chance here. So that's another reason why we can see numerically, what is 5? That would be related to the probability this and this. So the top is going to be the and. If B happened, the only way A could have also happened is if it was an A and B. Okay. We just developed another formula after we did a probability question. You guys see that? You're not used to this. You're used to, here's the formula, y equals mx plus b, and then you plug shit in. But what we just did was we did a problem using the basic idea, looked at what we did, made a formula. That is actually the way that a lot of stuff happens in mathematics. Believe it or not. All right. So now we can develop a formula for and. And this one is, I will tell you, this one is the freakiest kind of one. Does anybody see how algebra will help me get a formula for and? Do we have and in an equation somewhere up here already? Right there. There it is. Cool. So how do I get a formula for it? Well, I just have to get it by itself. Yes? Yes? So how do I get that by itself? Multiply by PB. I love it. Peanut butter. You gotta know a little bit of algebra. Just that much, right? So now I have the formula for probability of A and B is equal to probability of B times probability of A given B. That's exciting. No, it's not. Don't worry. It's all right. So look, here's the formula for Oregon. Let me put these two up here because these guys seem to be always kind of opposite ideas in a way. OR is basically add. Why does it make sense? Because OR increases the chances I'll match with something, right? It's a nice bouncer. And is basically multiply. Now here's where something, I know I'm a math guy, but this has got to be interesting just to more than just me. Normally when you multiply two numbers, does the result get bigger or smaller? Bigger. 2 times 5 is 10, right? What happens when you multiply two numbers that are less than 1? What's 0.4 times 0.4? 0.16. Do you see how the result got smaller? So the one time you multiply two things and the result gets smaller is if they are between 0 and 1. And I know you guys might not be the most interested in this, but I seem to be going to do this anyway right now. Here's a straight line. That's amazing. 1, 2. You guys with me? That's amazing, right? What's a parabola look like? And what's it come from? Parabola. Parabola. X squared. So isn't that what we're just now talking about? If I multiply two things that, something times itself is less than 1, look what happens. Doesn't a parabola bend down here? So right in here, the results are smaller for numbers that are between 0 and 1. And then once you get to 1, it's equal, and then past 1, 2 times 2 is 4, it's bigger. Amazing. Sorry, couldn't stop myself. You guys are sitting there like, my life is going to be the same now, I know that, Jeff, but I don't care. I just had to do it. You guys, it's neat. If you've never noticed that about the graph, it actually confirms what I just said. So, look what this does. We know that and should make things smaller, right? Just like the scholarships, just like the and bouncer, less people can get in there. Less people can qualify for the scholarship. And when you multiply two decimals, you get smaller. Bam! Kick ass. Maybe. Could be. It's possible, Jeff. All right. Now, yeah, I can do this. So there's two big formulas, and there's the third one. Yay, those are the three big formulas for this section right there. All right, let me do one more thing with this. What was the probability? What's the probability somebody said no? I always get at least one person. Is everybody cool with my little Roman numerals? You guys all right? VII. I always get somebody like, is that part of the? No, that's the seventh little example. What's probably somebody said no? 38 out of 81. Somebody help me out. What is that? I'm sorry? 469? Yeah. 469? Oh? Yeah. I guess? Okay. All right. That's now, all right, so. Real quick, we've done a lot, right? You guys feel like we've done a lot? We have. So what I'm trying to do is I'm laying a lot of groundwork, and this is the last really key piece that is the most difficult for people to kind of get, but I'm always hopeful. The probability somebody says no is almost 47%, right? What if I knew that person was under 21? Does that change the probability they said no? We already calculated that. Where are you calculating? What is the probability? If I know that they're less than 21, so where have we calculated that? What's probably they said no if I know that they're less than 21? Right there. Does it change? Yes. So would you say that the probability of them saying no depends on how old they are? If they're less than 21 or greater than equal to 20? Of course you would. Of course, because a freaking number changed. I like it. I like it. So in general, if the probability of A given B is equal to the probability of A, this is independent. If B happens and A doesn't give a shit, the probability of A given B is the same as what it was before, then that means that B happening didn't affect A. They're independent. But in this example, does knowing how old they are change the probability? I said no. Yeah, it goes up. It's a higher chance. This is something called a conditional probability. This is huge. We use these all the time. Given that is this time, what's the probability I get home in less than an hour? Not good. All right, I'm just going to have a few more drinks and wait. Maybe not too many drinks. You safe, kids. All right. Real talk. All right. So we got one more situation, and then we'll head out early. Okay. Well, somebody has a problem with that. So these three formulas, you could just add to your formula sheet. If you lost points on the formula sheet, what the hell? Don't do that. You can't get those points back. Too bad. So just next time, maybe don't write stuff on your formula sheet you're not allowed to. So I want to look at this a little closer. For a minute. We already know the formula for this, but just to really hammer this home. We know that and basically means multiply. But let's see it. I have a very serious example and a very silly example for this. So in 1986, young Jeff was in English class in Florida. We normally would go out to watch the shuttle take off, but that day we didn't for whatever reason, and then we found out it blew up, and I still see exactly where I was because I was such a huge geek. I was all about the space shuttle. So when it blew up, I was just crying. You know, I think there's a couple other people crying. The rest of them were like, suck it up. People died. But anyway, so you guys know about that? I know that was like prehistory for most of you guys. But that, and it happened again. It's like, shit, well, which time are you talking about when the shuttle just blew up? I hate that we say that now, but oh well. That first time it blew up. Again, sucks to say that. Do you guys have any idea why it happened? Anybody know why it happened? Beautiful. You know, that's the wrong word to use, but yes, that's right. There's these things called O-rings in the fuel line. And they're basically valves to make sure that it goes one direction only. And normally the probability that they fail was really small. So it's smaller than this, but just for our sake, let's say it was a 10% chance that it fails. Actually more like a 1 out of a million chance or whatever. 10% chance it fails. Why would they have multiple of them? Why would they have several of them? If you live in a bad neighborhood, do you have one lock on your door? If you have a test really early, do you set one alarm? All of these situations are... Yeah, so what is the other O-rings, the other clocks, the other locks? They are all backup plans. Backup plans. right? You guys with me? Obviously then, and can't be add, because then if you added these, now it's a 20% chance of failure. Oh, why did I do that? Put more locks to the door, the robber's just like, well, thank you. Much easier to get in now. So obviously it can't be add, and of course, well, it's 0.1 times 0.1. And why would we do that? How often will this fail? 10% of the time, right? Of those times, of the times that guy fails, how often will this guy also fail? 10%. So 10% of 10%, and of course we know of means freaking multiply, right? Yes, we do. If you say so, but it used to be a thing everybody knew. And what is 0.1 times 0.1? That's right, kids. 0.1. Thanks for all the help. When you multiply by 0.1, it gets 1 decimal place smaller. What do you do when you multiply by 1? When you're actually dividing by, what is 0.1 as a fraction?
1 over 100.
1 over 0.1 is 1. I'm just going to crawl under the table. 0.1, 1/10. You guys, everybody with me? Yes, okay. So 1/10 of something just moves the decimal back 1 place because our number system is based on 10. I don't know why. Okay, I like it. So again, this is more of a conceptual approach as to why and can't be add, because then if I put multiple locks, it would be easier for somebody to get in. That doesn't make any damn sense. All right, maybe. The silly example really quickly. Let's say I want to join a fraternity, and they have a very light hazing, nothing that would get them in trouble. I walk down this hallway, and every 5th step I take, somebody slaps me on this cheek. And every 9th step I take, somebody slaps me on that cheek, right? How often will I get slapped on this and this? Every 5th step, bam. Every 9th step, bam. How often will I get slapped on both at once? You could do this. You can, you really can. Every 5th step, bam. Every 9th step, bam. So how many steps until I get hit on both cheeks? Say again? No. Would I get slapped on the 14th step? This cheek I get slapped on what? 5th, 10th, you with me? 15th. This one, 9th? 45th? Yes, 45th. So if I get 1 slap every 5 steps, 1 slap every 9 steps, how often do I get slapped and slapped? 1/5 times 1/9, 1 out of 45. There's another application of why it's multiplication. Okay, all right. Stop. So, what does this mean? This is the last problem we're doing today. All right. Let's go back to this. I got just poker chips because I don't have any creativity left at the moment. Let's say I have 4 red, 6 green. 6 is the wrong number for green, Jeff. Good point. 7 green and 5 blue. You with me? So if I picked 1 poker chip, what's the probability that I get a red poker chip? 4/16. I like it. 25%, right? That's 1/4. That's 25%. Bam. Shwa. Now, let's change it up. What if I pick 2? There's a couple ways I could pick 2, isn't there? One, I could pick 1, drop it back in, and then pick another one. We call that, because we're so creative as math people, we call that with replacement. Pick 1, replace it. Pick another one. So I could pick that same one, couldn't I? Or the other way I could do it is to pick 1 and then feed it to my little brother. He had a lot of medical trouble. I don't know why. What does that do then? Before I pick the other one, what changed? The denominator. Yeah, there's less chips in there. Okay, so let's do one problem both ways. So pick 2 chips. The first one is with replacement. meaning I drop the first chip back in. What's probably I get a blue and then a green. So there's an and there, right? And there's two situations. I'm going to multiply these. Probably the first one is blue. What is it? What's probably the first one is blue?
5.
Blue. 5 out of 16. And then I put it back in. Now what's the probability the next one's green? 7 out of 16. I like it. So if I would have picked 3, 4, 5, 6 chips, it's not hard to set that up. And means multiply. 5/16 of the time I'll get a blue, and 7/16 of those times I'll also get a green. Of means multiply. And then whatever the hell that is. 35 out of, I used to know what 16 squared was. 256? 256. Is it 256? Yes. And then whatever the hell that is. I don't know. I don't know. I don't know. It's about 11% maybe.
1.136.
What is it, sorry? 1.
1367.
1367? Okay. Thank you. Now, here it is, the last piece of the last problem. Here it comes. If I do this without replacement, become a normal word. There you go. Same question. Probably get a blue and then a green. So nothing's happened yet. I reach in, I take a chip, what's probably is blue. 5 out of 16. Then I throw it away. And my little brother still eats it because it's weird. I got 2 little brothers. It could be either one of you, so if it's you, it's not you. Don't worry. Now let's probably get a green on the next go. 7 out of 15, because there's one less chip. Right? So if I had another one, the bottom would become 14. And another one, about 13. I like it. Why does the bottom only get down to 15? Because I'm only picking 2 chips. I haven't picked anything yet when I write this number down, and now I've picked 1 chip before this one. People will sometimes make this become 11 because they subtract 5. That doesn't make any damn sense. I'm only picking 2 total chips. Are they all stuck together? Right? Again, because my little brother's sticky hands got in there. And then, let's see, what is that? 1/3 of 1/2 is like 1/5, some 0.15 something there? I don't know. Nobody's going to help me out. What is it? 1.458. Which rounds to 1.5? Yay, Jeff. All right, I'll stop. Oh my gosh. So, which section did we just do? A lot of them. Which section have we finished? I don't know. This is sort of an overview of chapter, what is it, 3, right? Probability. Next time I'm going to have, I got to finish out a few details, and I'm going to have a little worksheet that you guys will work on together. And then I might have the practice quiz. This is the one time I give a practice quiz out is for the double quiz. All right, that's enough. Whoa. Maybe else back, get their chest back. Oh yeah.